to assign probabilities to regions. Okay, let me to other regions. Of course, omega itself will have probability 1, okay, always it has to have, to regions. We start with or we define a function which we call the joint density, joint PDF. So what is this joint PDF? It takes you from basically all of r squared to the interval 0 to infinity. I mean it is a non-negative function on xy, such that what the double integral can, so it's only just that I have to bend down a little bit. So this double integral over omega, so you have defined, right, already defined this the sample space for the experiment. So we have to make sure that this function has unit volume when you do a double integration, and also there are smoothness constraints on this f. You do not want it to be some totally crazy function which jumps around all over the place, right. Some discontinuities here and there, especially the boundaries, is okay, as we will see. We will look at examples, so f is not completely right, it is not allowed to be totally funny, right, it has to be minimally smooth in some sense, but I don't have a mathematical way of putting it down, so I am not going to write it here, but just keep that in our heads, right. F cannot be arbitrarily allowed to vary. Especially this double integral must make sense, and not only for over omega, right. So we do a domain extension. First of all, we define that how are we going to define this fxy over the entire plane? Obviously by saying that it will have non-zero values only in omega, and outside omega it will have 0. That is the first thing we have to do, right. So for uniformity's sake, all PDF, like all univariate PDFs were defined over the whole real line, all this double joint PDF will also be defined over the whole plane. So right, so what do we know? We know that fxy xy of the value of this is, it's first of all, as like in the 1D case, it is not a probability, right, it is only a density function. So this fxy xy is greater than 0 only, of course it can also be 0, but it, right, only when xy is in omega, right. So and so you do this, so this is domain extension, right. To r squared. For example, when you consider the darts experiment, it makes no sense to say that the sample space is the entire xy plane, right. It is typically taken to be some circle with some finite radius. So what do you say the joint density function? It takes non-zero values only inside that circle, such that this is satisfied. So now can we claim this statement? Every region of R squared will have a probability. It can be 0, it can be unity. Yeah, right, we can say that now, right, without any problem. Every region of R squared can be assigned a probability. If the region of R squared that we are interested in is totally outside capital omega, then it corresponds to a null event, probability 0. It's as simple as that. If that region includes omega completely, then it is a certain event with probability 1, isn't it? So every region of R squared will be assigned a probability based on this F, this joint PDF. So, okay, one more thing I want to say is that, right, this is not the only way in which you can do it, right. This is the most practically important way, that for engineers as we are, we care a lot we care mostly about situations where regions in R squared have, right, probabilities assigned through a joint PDF, but that is not the only way. So, let me write it here. I was like, maybe should I use the word, okay, I will write warning, right. Joint PDF not the only way to assign probabilities, right, but it is the most practically significant, most important from an engineering point of view. So, what does this remind you of? It reminds you of the PDF and the CDF conflict that we had with the single random variable, right. Do you use a CDF to assign probabilities? Well, you can do that, but it's in general it turns out to be not as important as starting with a PDF from an engineering, again from an engineering point of view. And all our engineering problems we encounter, we love PDFs, we do not care so much about, and even here there is a CDF that we have to look at, right. So, what is, so I will write here CDF versus PDF, right. So, here in the 2D case all books will not talk about straight away talk about the joint PDF, instead they will say we will start off with something called a joint CDF. What is a joint CDF? So, as I say, so we have to, so now that we have understood the joint PDF, does anyone have any problem with the joint PDF? Right, yes, you have a non-negative function which is reasonably smooth, right, you have defined it for so that it has this property. You first of all identified omega, you have identified, then you have identified a suitable function which has this property, right, and is nowhere negative. By the way, why can't PDFs be negative? I think the answer should be obvious, right. If you look at a very small interval or a small region around where it is negative, you can get negative probability. So, you cannot ever allow negative values in PDFs, that is all, right. Even though it is not itself probability, you cannot allow negative values, it has to be positive. Then of course, right, this one is just normalization, all you care about is that this integral is finite. So, everyone is okay with this, right. So, what is a joint CDF? I am sure those of you that have studied, what particular region are we looking at for a joint CDF for two random variables? The joint CDF is this event, this region minus infinity at for joint CDF at, let us say, or for x naught, some you pick a point x naught y naught in the plane. It is basically minus infinity to x naught, or maybe I should use I should not use this, I will use random variable notation itself, capital X less than x naught, and I will put an and here which is all basically a comma does not seem to have quite the same impact as writing that and, but please remember that, right. So, anytime you use a comma it is a very firm A and D, and what, right. So, what is this? It turns out that this is what region? It is another region, right. What is that region? So, this region is completely oblivious to capital omega, right. You just define some, right, the definition does not care about the actual experiment at all. It just says, well, somehow you are supposed to look at that, and that too, vary this x naught for, you are supposed to do this for all x naught y naught in R squared, you are supposed to somehow magically define this number, okay. I mean I haven't defined the CDF yet, so it should be the probability for that region, right. So let me write it here. So if I pick some point x naught y naught here, without any regard to capital omega, if I just consider this region and say that this capital Fxy, so this is joint, let me write here the joint CDF capital Fxy x naught comma y naught. Again I am just using random variable notation here, not set notation, right, which is of that event with and okay, we should put the braces here for consistency, right. So this event, right, so somehow, right, magically that region is supposed to be assigned a probability, and that too for all x naught y naught in R squared, not just for some points. So it turns out that this is not a practically what use a simple way of assigning probabilities. Yes, theoretically, it can take care of curves, it can take care of, right. The PDF approach has the limitation that it cannot handle points and curves so nicely, but it can handle regions perfectly well. That is what we want, right. This is more general in that yes, it can handle everything, but it is, right, it is not very, in my humble opinion, right, it is not a good starting point for any engineering problem. Just like in the 1D case, nobody ever starts off with, okay, this is the CDF, so what do we do with it, right. In most engineering problems you want, right, okay, so just for completeness sake we should be aware, right. So this is basically, of course when the joint PDF is specified you can always find this probability by integration, right, it is not an issue. What would be the limits of the integral? Minus infinity to x naught, right. So okay, I did not write, maybe I should have written that here. So the using a joint PDF, what is the probability of a region? You write this xy element of D, some region D, right, is basically the double integral over D fxy xy dx dy. So maybe, right, this should have come a little ahead of this, but when I want to say lots of things I forget. So I have only defined, okay, I think everything is there on this piece, right. Just remember that this should have gone here. Before talking about joint CDF I should have written this. So this, okay fine, now coming back to this. So if you have a joint PDF fxy, how do I find this probability? I would integrate from minus infinity to, right, the limits would be minus infinity to x naught, minus infinity to y naught. That is all I have to do. So I can always get this from this. So this basically, so fxy x naught y naught, let me write it very clearly, is basically minus infinity to x naught minus infinity. Again we have to be careful about the limits here, right. If I say minus infinity to x naught, that means the inner integral is on x. So fxy, so when you do multiple integrals, so please review your, right, material on multiple integrals. You are not allowed to write this totally independently of this, right. This inner integral is dx and the outer integral is over y. So that order has to be maintained, because if you do not maintain that order you are going to run into trouble when you try to change variables and so on. All of this we have to do now, right. We have to go back to our notes or whatever material that we picked up on multiple integration, right, and keep it all ready for use, right. So if you have this is no issue at all. You can integrate using, if you can't integrate by analytically, you can always integrate numerically, right. It is not a problem. So it turns out that this joint CDF in general specifying it directly is a very cumbersome business, especially that it has to have certain properties, right. For example, it has to be non-decreasing in both, if you look at this, it has to be non-decreasing in both arguments, right. And then right, if you of course it is a probability, so this has to be always between 0 and 1, right, but mainly it has to be non-decreasing. It can but it can, you are in general you can allow it to jump in a way that this cannot jump. If you do it like this will be a smooth function of x0 y0 if this is well behaved. If the joint PDF is well behaved, this is not going to have jumps, just like the 1D case. But in general, let me say this is cumbersome to specify directly. If it was difficult enough in the 1D case, it is almost very painful to do in the 2D case, right, when you have possibly for example, if I have a funny shaped omega, if this is my omega, you can imagine now how this CDF is going to vary in this region, for example. How would you specify, even if this omega was a nice circle, it turns out it is not at all easy to write it down. And then if you look at some intersections of this half plane with omega, then you get even funnier functions of x0 and y0. So all told, just I don't think I write, you can fight me on this issue. That is, this from my experience is an absolute nightmare, even right when your capital omega is anything which is not aligned with the x and y axis. It is easy to do only in CDF is easy to deal with only if capital omega itself is a nice rectangle aligned with the axis. Any other case, right, because this capital F has no, right, does not look at omega at all, it is an absolute mess to specify for any other case. I have just written cumbersome, but I can say worse things about it, right, verbally. Because I have tried writing it and I found that just for maybe bringing it out as an example in a class, and I just gave up, right. It took me one whole several pages to try to specify it correctly in problem. Once I start doing it, I want to do it fully and correctly, and I found it was not worth the trouble. Okay, I think maybe, one last thing. Supposing this capital F is reasonably smooth and differentiable, how would you go from, supposing somebody gave you this function, right, with all the requisite probabilities that it is increase not, and I am not going to write them down, you can go read it up in a book. It has to basically, it cannot decrease as you keep increasing x0 or y0, it has to either stay the same or increase, because the region is always getting bigger as you increase x0 or y0. So how do you get this from this? It is basically the double derivative, right. So given capital F xy, the density function, if it is reasonably differentiable and so on, right, let me write it here, the density function at some point is basically, how do you what do you say, how do you write that, or how do you say that, d squared by dx dy, it's just d squared by dx dy, only when you write it using partial derivatives, right, of what, of that. This of course assumes, right, this should not jump at any xy. Okay, so we will stop here.